Hi everyone, I'm Charit. I'm a PhD student at MIT, and today I'll be talking about how to build state-of-the-art compile optimizations with minimal human value. Compilers translate high-level language programs to low-level languages which can be directly executed on hardware. And one of the goals of an optimizing compiler is to find one such semantic preserving translation that will also generate fast code. And usually, this is done using a number of different stages. First, the compiler translates the high-level language to an intermediate representation, which is next fed through a number of different transformation passes to arrive at an optimized version of it. And finally, this optimized intermediate representation is lowered down into machine code, which can be directly executed on hardware. And as of late, designing, developing, and maintaining these transformation passes, which are responsible for compile optimizations, has become complex. Now, compilers need to reason about how better to optimize millions of programs with different computational patterns, targeting a plethora of complex hardware platforms with different architectural capabilities. In spite of these complexities, however, compilers are still constructed using technology that existed decades ago. Compiler optimizations are still handcrafted and usually only follow one hard-coded optimization algorithm and are not that responsive to changes in the computing environment. And this design has a number of different disadvantages. Firstly, hard-coded compile optimizations can be fragile, and fixing them up can be even more tedious. To illustrate this point, let's look at compile auto-vectorization, an important compile optimization pass that you can find in virtually every modern-day compile out there. I compiled two different benchmarking applications and observed what the compiler would do in each case. For the first solver application BT, the compiler decided not to vectorize an important piece of code. Whereas for the second simulation application NAMD, the compiler was indeed successful at vectorization. However, if we manually reverse the decisions of the compiler and recompile it and re-benchmark the code, you can observe an appreciable performance increase in both the applications. In the first solver application, the encapsulating function got sped up by more than 3.7x, leading to an end-to-end application speed up of more than 20%. Similarly, in the simulation application, just by not vectorizing, the encapsulating function full elect got sped up by more than 1.7x, leading to an end-to-end application speed up of more than 10%. So next, I dug deep to find out why exactly the compiler made its decisions. In the first case, the compiler does not even consider it for vectorization due to a bad heuristic. And in the second case, the compiler makes an erroneous judgment due to a bad profitability metric. Okay, now since we have identified these problems, we can go ahead and correct them. But the way to correct it, according to the current way of constructing compilers, is to manually deploy two different patches. Mind you, these are two different code patterns that I found in the current compilation chain. But there may be thousands of other code patterns which are not properly handled by the compiler. And if you want to correct them, you may have to deploy thousands of other manually written patches. And this process is not going to be scalable and it's tedious to maintain. And as you already saw in the solver example case, manually writing compile optimizations passes can easily lead to stale optimizations. And updating them can be labor intensive. Also, they are susceptible to modeling errors in handwritten performance models, as you saw in the simulation example case. In fact, LLVM's Intel performance model is actually maintained by Sony with mainly access to AMD hardware and is not properly validated. And our studies show that this performance model has an error of almost 20%. So compiler writers do not trust these performance models. And most of the important advanced compile optimizations are turned off by default without a good profitability metric. With all of these problems, I suggest that we need a better way to construct compiler optimizations. To see how we can do that, let's look at what has changed in the computing environment around compilers. Now developers develop millions of programs, and we have access to better optimization algorithms or solvers, be it discrete or continuous. And most importantly, we have access to complex and powerful hardware systems. So my solution is to leverage the changes in the computing environment to go towards more automated ways of constructing compile optimizations, which not only achieve state-of-the-art results, but will also reduce the burden on human development. Okay, to see how we can achieve this, let's look at an example compile optimization pass in more detail. If you zoom in to this pass and look at its decision-making components, you can view it as an interplay between three different parts. First, the compiler needs to know what transformations are legal for it to make. And this is usually encapsulated as a transformation space, or rather a subspace of all semantically equivalent transformations, which the compile optimization pass is intended to do. And next, the compiler needs to know how profitable each transformation is. And usually this is exposed through a cost model. And finally, at the heart of the compiler transformation pass is an optimization strategy, which traverses this subspace to find one such profitable transformation. And the efficacy of a transformation pass depends heavily on how realistically you model these three components. Ideally, you want to use ground truth runtime instead of a cost model. And you want to use an optimal algorithm that will guarantee you can find the optimal transformation or the transformation with the least possible cost. But however, compiler writers approximate these components. Instead of using optimal algorithms, compiler writers use handcrafted heuristics. And instead of using the ground truth runtime, compiler developers use handcrafted simplified cost models to approximate it. In this talk, I will use my work on compile auto-vectorization to show how you can go from manually written heuristic solutions to more automated solutions to construct compile optimization, which can not only achieve state-of-the-art results, but will also minimize the development burden on the compiler developers. First, I'll show you how to perform compile auto-vectorization optimally with the aid of an solver, assuming the same linear cost model that modern compilers like LLVM uses. Secondly, I will show you how to learn compile auto-vectorization from scratch using data that has the potential to eliminate the need for having a handwritten optimization algorithm. And thirdly, I will show you how to develop better cost models, again using data, which can significantly outperform analytical cost models out there. And finally, I will convince that these data-driven techniques apply beyond vectorization and should be adopted for compiler construction in future. Okay, now let's look at compile auto-vectorization in more detail. There are two main flavors of compile auto-vectorization, namely loop vectorization and SLP-based vectorization. And in this talk, I'm going to focus myself on SLP-based vectorization mainly. The idea behind SLP vectorization is to coalesce or merge two or more scalar statements which are independent and isomorphic of each other into vector packs first, which is later converted into vector instructions during the compiler code generation phase. Here, what I mean by isomorphic is that these two statements should perform the same operation on the same data types. And if this is true, the compiler can vectorize code as long as the statements are independent. Therefore, one of the main challenges or problems the compiler needs to solve is to select which statements get packed together. First, to do this, compiler needs to know the transformation space of all available statement packing opportunities. To make it more clear, let's take a simple example. Here I show you a code snippet with two isomorphic groups of instructions. The first group does divisions on values loaded from array L to come up with intermediate values A1 up to A3. And the second group does subtractions on these intermediate values to arrive at the final values A4 up to A6. And if you consider the vector width of the machine to be 2, then you can select any two statements out of each isomorphic group to pack together. And this is the entire transformation space for this particular example. However, if you look closely, note that not all statement packs can exist with each other. For instance, if a particular statement is part of one vector pack, it cannot be part of another. So the final job of the compiler is to select the most profitable set of statement packing opportunities out of the entire transformation space of opportunities out there. And in this case, only two opportunities can be materialized out of the 6 I have shown here. Okay, now let's see an example statement packing strategy. Let's assume that the compiler selected to pack statements S1, S2, as well as S5 and S6 together. These are completely legal, so compiler can go ahead and emit vector code for this. But however, if you do a compiler transformation, it has to be semantic preserving. So in this case, compiler needs to see whether there are any fix-ups it needs to do. To make it more clear, let's look at this vectorized value A3 and A1 and try to locate its constituents. Note that A1 is already packed with A2 and is in vector form, whereas A3 is in scalar form. So they are not isomorphic of each other and are not amenable for vectorization. So to correct this situation, the compiler needs to first unpack A1 out of its vector pack and repack it with A3. And this incurs the overhead cost of 2 instructions. And if you go about fixing up all the code, for this particular vectorization strategy, the compiler needed to emit 3 overhead instructions. Okay, now let's look at an alternative vectorization strategy. Instead of selecting S1 and S2, let the compiler select statements S2 and S3 to vectorize. And instead of S5 and S6, let's assume that the compiler selected statements S4 and S5 to vectorize. And in this case, if we follow the same vectorization strategy, we can show that the compiler is able to emit 5 vector instructions and only incur a cost of 2 additional overhead instructions. Okay, so even for this simple code snippet, based on the decisions made by the compiler, the profitability changes drastically. Actually, the first strategy follows a heuristical algorithm that is suggested in literature, and the second strategy can be shown to be optimal in this case. So a natural question now that we need to ask is, how hard is statement packing in general? Remember that what I have shown you here is one basic block out of many in an end statement function. So if you consider one statement and only consider pairwise packing, then there are order n amount of opportunities. And if you consider all statements together, then there are exponentially many opportunities. In fact, you can show that statement packing problem is a special case of the optimal subset selection problem, which is known to be NP-hard. So researchers have been suggesting greedy algorithms or heuristic driven algorithms mainly to solve this problem. And there have been attempts at doing local searches on a limited instruction window of statements. Okay, now I'm going to show you how to perform SLP-based vectorization optimally with the aid of a solver. More specifically, we reduce the statement packing problem into an integer linear programming problem, which is solved for whole functions at a time, arriving at a globally tractable result. The idea behind the formulation is simple. What you want to do here is to encode the benefits and the costs of vectorization into the objective function of the ILP formula, and then you can use an off-the-shelf ILP solver to do this. But if you naively encode the problem, it's not going to be feasible for the ILP solver to do the search. In fact, representation matters a lot for the feasibility of your solution. There have been original attempts at forming SLP vectorization or statement packing problem as an ILP problem. Specifically, I will go into one. This is from Larsen's original thesis on SLP vectorization. He tried to formulate the statement packing problem for an entire path of vectorization opportunities. And this resulted in an encoding complexity which was exponential in terms of the number of statements in a function. And if you follow this strategy, even for a representative benchmark, it will take more than 24 hours to compile or to solve the problem. So can we do better? So if you look at the problem more closely, you can see even though we are solving a global optimization problem, the benefits and costs of vectorization or statement packing can be encoded locally. More specifically, benefits only depends on the statements that get packed together, and the cost only depends on the users and definitions of those statements. So therefore, with this insight in mind, you can now do a local encoding of costs and benefits per pack and still use the ILP solver to do the global search. So our solution, GoSLP, reduces the encoding complexity to be quadratic in terms of the number of statements out there. Even in the worst case, for a 40 file function, this particular encoding can results in ILP solution which can be solved within 8 minutes at most. So this is feasible. Okay, now I will quickly touch base on how you can go about encoding the solution as into the objective function. Again, I will take the same example I took before, and this is the transformation space for this particular code snippet. And once the compiler has enumerated the transformation space, then you can go ahead and create decision variables for each and every opportunity for statement packing. And these decision variables are Boolean signifying whether you pack the statements or not. And once you have these variables, you can encode the costs and benefits of vectorization as a linear combination of them and solve it subject to certain constraints. And one of those constraints is like a particular statement cannot be part of two vector packs. And we formulate this problem for two statements at a time, arriving at a pairwise optimal statement packing, and we iteratively apply this procedure to cover the entire width of the vector width of the machine. I implemented this in the LLVM compiler and tested it out on Spec 2017 FP, Spec 2006 XP, and NAS benchmarks. And here I show you some results. Mind you, these are not simple kernels or loops. These are end-to-end program speedups, and in some cases, we are able to achieve more than 16% speed up on programs which have more than 250,000 lines of code. And here I summarize all the results in a graph. The y-axis shows the speed up that we can achieve over the LLVM compiler for all the benchmarks that are listed in the x-axis. In summary, GoSLP or the ILP-based solution is able to achieve more than 7.58% speed up on Spec 2000 FPC and C++ programs. And if you are not familiar with spec benchmarks, to put these results into perspective, Intel's major microarchitecture revisions actually achieve around 20% on the same benchmark. So you can think of our improvement as 40% of what Intel would achieve with $1 billion investment. And moreover, our ILP solution automatically corrects the code patterns which were incorrectly vectorized or not vectorized that I mentioned at the beginning of my talk. Okay, now we have a good enough solution. So are we satisfied? But if you look into the solution a little bit further, you can identify two undesirable characteristics of it. First one is, since we are using an ILP solver, the solution times can be unpredictable. And the second is, like, even if we want to go beyond a linear cost model, we cannot with the current formulation. So we need a framework which can automatically extract all the good decisions taken by the ILP solution, but also it should be extendable beyond linear cost models to capture arbitrary cost models that we can develop in future. So this is where end-to-end learning of optimization policies can help. The next part of the talk, I will show you how to learn vectorization from scratch using data or experiences. Okay. So if you step back and look at the problem that we are going to solve, we are going to learn how to translate a scalar representation of the program into a vector representation of the same program. So this has the flavor of translating from one language to another. And maybe we can use something like machine translation, which is prevalent in natural language processing. But however, this does not quite work because unlike in NLP, we have to guarantee correctness in any compiler transformation. So what instead I do is I exploit the compositional structure of the transformation. Compiler developers have been exploiting the composition structure mainly at the parse abstraction level. Instead of writing the compiler as one monolithic object, you write it as a set of parsers which are applied sequentially one after the other. And the sequential application still preserves the correctness of the code. And if you look closely at an individual parse, this particular compositional structure is still there, but it is implicit. So my solution is to expose it. More specifically, rather than thinking of compile auto vectorization as one monolithic parse, you can think of it as vectorizing one statement at a time until you reach a state where there are no more vectorization opportunities out there. Okay. With the compositional structure exposed, now we can actually model or compile auto vectorization as a sequential decision making process, or more technically as a Markov decision making process, similar to how AI researchers have solved board games or have modeled board games, which they have solved using techniques like reinforcement learning or imitation learning. So to see how we can do this, let's take the same example. You can think of the initial scalar program that you receive as the initial state of the process. And then for a given statement, we are going to expose all the valid statement packing opportunities as the action space. And from this action space, a learned agent will take one valid action. The key here is the action is always valid since we are enumerating only valid actions. And once it has taken action, you can go ahead and mutate the code so you can arrive at a partially vectorized program. This is going to be a new state. And now you can consider this as your state and apply this process iteratively until you reach a terminal state, at which point you can run the program to see whether you have done a good job at vectorization. And this can be part of your reward function. Okay. So now we have a MDP formulation for vectorization. The next thing is to design an agent to take the valid action for a given state. And the strategy we are going to follow is to use imitation learning to follow what the ILP solver is already doing. This is to extract the experiences that the ILP solver was good at, but at a cheaper cost. So the first step of in doing this strategy is to collect demonstrations or to collect experiences. So for a given program and a given state, and for a given statement, we are going to ask the ILP solver or the ILP formulation of the vectorization problem what to select what it's going to do for vectorization. Assume for statement A1, the Oracle selected it to be vectorized with A2, you can go ahead and mutate the code signifying its decision. Now we are going to collect the initial states as well as the action that the Oracle took into a state action pair buffer. And we fill this buffer using all the programs and all the states that we can see in our training set. Okay. Now we have the once we have this buffer, we can use it as a supervised data set to learn a policy network to select the best set of action to take at a given state. To make this process robust, we are going to augment our data set at each epoch using a well-known algorithm in AI literature known as Dagger. The reason being, if you only collect experiences from the optimal policy, and if the neural network makes some erroneous judgment, then it does not know how to recover from it. So we are going to extend our experiences and augment our data set at each epoch with policies that runs out of the optimal trajectory so that it can recover in future. And this is a well-known data augmentation technique in AI literature, and we are adopting it into our to make our learned policy more robust. Okay, now we have the training regime properly set up. With that, let's see how we can represent the program into the function approximator that we are going to use. The most naive way to do this would be to feed the program as text, but that does not quite work. And in fact, representation of the problem matters a lot here, as in the case of the ILP solver, not for tractability, but for learnability. And another goal that we have in designing these systems is to make it as easy for the compiler developers as possible. So we selected a naturally occurring representation as our state, naturally occurring representation of the program as our state representation. More specifically, it is the program dependence graph. So once you have the program dependence graph as your state, then you can select a particular statement, say A1, and ask the neural network whether it's better to vectorize it with A2, A4, or not to vectorize at all. And say that the learned agent selected it to be vectorized with A2, we can then mutate the graph to signify or to denote the decision taken by the learned agent by adding in vector nodes. And you can iteratively do this process by selecting the next node with vectorization opportunity. And since we represented our state as a graph, we are going to use a graph representation of a neural network known as a gated graph neural network. Here, an important thing to note is that there is a one-to-one correspondence between this between a node in the state representation and a node in the graph neural network, and we do not require any featureization from the developer to make it work. So this is the objective here is to make the development effort as minimal as possible. So with that training regime and state representation in hand, next we tested out whether we can learn a good enough policy. To do that, I collected a bunch of experiences from Spec 2006, Spec 2017 programs, and trained the neural network or the learned agent and tested it out on NAS parallel benchmark suits. And here I show you results for both the ILP based solution as well as the learned agent Vimal, where the y-axis shows the speed up of it over LLVM's own vectorizer. So anything above 1 means that there's a speed up over LLVM. And if you closely look at the results, for 5 out of the 7 benchmarks out there, the learned agent matches or exceeds the performance of the ILP based solution. So that's good. That means the learned agent is performing well. But there's something fishy going on. It's okay to match the performance of the ILP based solution. But how can the learned agent, even when it considers the ILP based solution as the oracle, exceeds the performance of it? That's counterintuitive. So let's look at the results again. And if you look closely, there are instances where the heuristical LLVM solution is actually better than the ILP based solution, even when it's optimal. And as I've already shown, the learned agent consistently outperforms the oracle or the ILP based solution in certain benchmarks. So the biggest question here is, how can the optimal ILP based solution be slower than any system? To investigate further, I did another experiment. I took all the unique loops out of Spec 2017 FP programs and ran it without vectorization, with LLVM vectorization, and with ILP based vectorization. And for each vectorization strategy, I computed the percentage reduction in runtime it has on each individual loop and tabulated it in this graph. So here in the y-axis shows the percentage reduction in runtime compared to the scalar code. So anything above 0 is good. And if the ILP based solution is truly optimal, the red line should be strictly above the blue line, or should be at least above the blue line. But here, as you can see, there are multiple dips in the red line. So this begs the question, is the ILP based solution actually optimal, or more correctly pairwise optimal? It is, but with a catch or an assumption that we are using a linear cost model. But if you look at modern day microprocessors, their execution patterns are highly nonlinear. More specifically, they are superscalar, pipelined, out of order machines. So trying to model it as a linear model can only go so far. So this necessitates the need to have more accurate cost models or more accurate nonlinear cost models. Now I will show you how you can use data to learn a more accurate cost model that can significantly outperform analytical models out there. Actually, accurate modeling of a process is a hard job. Even the most sophisticated analytical cost models out there, like LLMs on LLM MCA, as well as Intel's on Ayaka, has an error rate of almost 20%. This is because if you want to get a correct prediction, you will have to model all the intricacies that are involved in a modern day microprocessor. For instance, you will have to model the micro caches, port contentions, port mappings, load store buffers, etc. and etc. And aggravating this fact, some of the implementation details are held proprietary by the vendors. So it is virtually impossible to get 100% accurate prediction. So the methodology these analytical model writers use is to consult thousands of pages of vendor manuals and to translate that into a specification inside the compiler that can quickly say how fast a particular piece of code would run. And as you can see, this process is tedious both to develop and to maintain. And it will inevitably, there would be human errors involved in this translation process. And there would be inevitably be modeling errors because processor vendors are not going to put in all the implementation details in these vendor manuals. And our approach is drastically different. Without trying to analytically model all the intricacies, we are going to use data to learn a model to predict the cost of running a particular basic block. And we show that by using a properly crafted function approximator, we can achieve significantly more accurate results. Here, our neural network architecture design had two different goals. First one, we want to make it as simple as possible for the compiler writer to maintain across multiple architectures. So we wanted to keep the same interface that was exposed through the analytical models. More specifically, we assume that the model will take row assembly instructions as input and will predict a real value throughput prediction as output. And our neural network architecture requires no featureization. It just requires as input the row assembly instructions. And this minimizes the effort that's needed for the compiler developer to maintain and to write such a system. And secondly, as in the case of the learned vectorizer, representation matters a lot for learnability here. We tried out a bunch of representation, but here I'm going to show you the representation that performed the best. More specifically, we used a hierarchical recurrent neural network formulation. Once you get the row assembly instructions as input, first you are going to tokenize it into operands and opcodes. And for each of these tokens, we are going to learn a high dimensional embedding in a high dimensional vector space. And in the next layer, we are going to summarize all of these token embeddings for each individual instruction using an LSTM layer to arrive at an instruction embedding for each individual instruction. And in the final layer, we are going to summarize the instruction embeddings for each and every individual instruction into a block embedding using another LSTM. And note that these two LSTMs are different and weights are not shared between them. So this is different from a traditional layered LSTM architecture. And once we have the block embedding or the final hidden layer for the block, we run it through a multi-layer perceptron to arrive at the final real value throughput prediction. To train this, we collected more than 1.4 million basic blocks out of representative benchmark suits as well as end-use applications and ran it on bare metal to collect the supervised dataset. And with the code blocks and their timing values properly listed out in a supervised dataset, then you can use any supervised learning technique to learn how to predict throughput using the neural network architecture that I have already mentioned. And next, we tested it out on held out test set. And these are the results for three different Intel microarchitecture. Here in this graph, I show you in the y-axis the average prediction error for three different systems: analytical models LLVM MCA and Intel's own Ayaka, and the learned model Ithama. And if you look closely, for the three different Intel microarchitectures that we considered, Ithama more than half the error rate of the analytical models out there. So this shows that the learned model can accurately predict throughput of basic blocks in a more portable manner. Okay, so the next task is to actually use this to make better optimization. So far, what we have done is we have used the sequential decision making formulation and trained how to take the best action for a given state using the ILP solver as the oracle. And more specifically, we use imitation there. But with the learned cost model in hand, now we can use it as part of the reward function to learn how to vectorize using reinforcement learning, which is some ongoing work that we have currently. So formulating compile optimizations as sequential decision making processes apply beyond vectorization. For example, even for low-end compile optimizations like register allocation. The way we can construct a MDP for register allocation is like this. You can treat a partially register allocated program as your state. And then for a given set of virtual registers, you can expose the set of free general purpose registers from which the learned agent can allocate a register. Next, you can mutate the code according to what the learned agent proposes to reflect its choice to arrive at a new state. And if you iteratively apply this process, you will arrive at a fully register allocated program, at which point you can run the code to see whether the strategy has been beneficial or not. And this sequential decision making paradigm applies even to high level optimizations that you can do in domain specific languages like Halide. If you're unfamiliar with Halide, Halide is a language where you can specify the algorithmic specification separately from the optimization space. So the way you would go about formulating IMDP for Halide auto scheduling here is you select a particular statement and expose all the optimization opportunities out there for a learned agent to pick. And once it picks a particular valid action, you can go ahead and augment the current schedule with that valid action. And if you do this process iteratively, finally you will reach a state where all the statements are scheduled properly, at which point you can run the program to get a reward. And I believe, in summary, that these data-driven techniques have the potential to play a major role in development of compile optimizations in the future. As I've showed you in vectorization, and as I have showed you how to model register allocation, as well as like high-level optimizations like auto-scheduling of Halide programs. So far, our work has impacted number of bug fixes in LLVM compiler. And we are also pushing in the new methodologies slowly into the compiler community in collaboration with the Google x86 team. These technologies will take time to be adopted by the community, but we are slowly moving towards realizing our goal. The work I have done so far provides initial impetus towards achieving my vision of automating construction of compile optimization, and more generally towards building automated tools to enable better decision making in programming systems. Now, I will briefly describe future directions I want to take towards realizing my vision. So far, I have only worked on automating construction of optimization strategies and cost models for compilers. And now I want to explore techniques to see whether we can even automatically generate the transformation space. As an example, modern day compilers only use a small fraction of available x86 instructions. I want to explore if we can use program synthesis based techniques to come up with richer transformation rules to automatically exploit the entire transformation space, which can cover most interesting instructions in x86 and possibly the entirety of it. Also, so far my work has only explored different x86 microarchitectures. I want to expand it to cover other commonly used hardware platforms. Specifically, I want to explore whether we can have an abstract representation to express transformations which can capture architectural capabilities across different architectures like RISC-V, ARM, GPUs, or TPUs. For instance, can we express uh, programmable vector types as a primitive? Or can we express other branch divergence or other computational models as a primitive in this abstract representation? Also, I want to explore techniques to build cost models across hundreds of implementations of these architectural specifications. As I said, I also want to broaden my horizon beyond compilers in the long term to enable better decision making in programming systems in general. I want to explore techniques to automatically optimize systems spanning heterogeneous and distributed hardware and to make more precise program analysis decisions. So far, I have predicted basic block throughput on a given microarchitecture. To make better optimization decisions, we need to build better performance models, which can now take into account both data as well as the program, as well as complex execution environments like multi-core processing with complex hierarchical memory systems. And we should be able to predict rich dynamic properties such as branch frequencies, cache misses, TLB misses, etc. and etc. And to finally predict end-to-end execution times. I want to explore data-driven techniques to achieve these goals so that we can build tools with minimal human burden. This can be used for better optimization decision making in distributed computing, compilers, architecture design, as well as in database. Finally, throughout my talk, I stress the importance of representation of programs. So far, researchers have been using graph neural networks to capture entity relationships in programs. I want to explore further to see what architectures would enable us to capture global properties, rich semantic uh, relationships in a language agnostic manner to not only make better program optimization decisions, but also to enrich other programming language tasks like program synthesis or other program analysis tasks. With that, I want to thank all of my collaborators and co-authors who have made my journey in graduate school enjoyable and more fruitful. Okay. And in conclusion, in this talk, I have shown you methodologies on how to go from manual, handcrafted solution to automatic means of constructing compile optimizations. I believe data-driven techniques will play a major role in development of automatic program optimization systems in the future. Thank you.